Today we're talking about machining processes, and this is an overview of several machining processes. We're going to go through 8, not that that's the limitation. There are more than 8 machining processes, but these are 8 very different machining processes, and we'll look at the differences in terms of the tool, in terms of the chip that it creates, removes the material. So we'll compare these 8 different machining processes that we're going to look at here. Let's define machining. Machining is the controlled removal of material from a workpiece to achieve a desired final shape and size. We've talked about additive manufacturing, but machining processes came far before additive manufacturing, and only later were machining processes called subtractive manufacturing because they remove material. Now, when I was working for a manufacturing company, I was working on the forgings, and we had a joke between our forgings and the plant, the rest of the plant where they did the machining processes, and we said all you do is take our forgings and you make chips out of them. So one of the things that machining is known for is making chips, making metal chips, which are the little pieces of metal that are gouged out by the machining tool. And then at the end of a machining process, usually you have a pile of those chips. We can call machining processes chip making processes. Those are the small pieces of metal that are cut off from the workpiece. So what is machining? It's the controlled removal of material from a workpiece, again, to get to the final shape that you want. It's subtractive. We said that. It's not limited to metal. Machining can be also applicable to plastics, wood, rubber, paper, etc. And there's a broad range of subtractive or machining processes. There are mechanical processes that we're focused on here in this lecture, like sawing, drilling, lathe turning, boring, milling, plating and shaping, broaching and grinding. So we're going to look at those. I have a quick video showing a milling process. We'll see that later. There are also removal processes by burning with energy sources like laser cutting, oxy-fuel energy, plasma. And this is a picture of a plasma process where you can program in the shape, and the torch or the tip will follow that shape. You can also, so this is a flat bed here, and the plasma is cutting through a piece of sheet on a flat bed. You can also use this same approach for water jet cutting. Imagine this tip is a water jet cutter, or laser cutting. So there's also programmable beds for big pieces of sheet like this for laser cutting. I mentioned water jet, so here's the water jet. It has a spray of water, usually for metals. The water is going to have some abrasive particles inside it. So at high speeds, those abrasive particles are pushing through and cutting little chips, making tiny little invisible sized chips out of the metal and leaving a cut behind. So water jet is actually not very expensive. It's available here in Sulaymaniyah. I believe. I know plasma cutting is. I've seen plasma cutting processes at Azadi Industries, and several other places have plasma and laser cutting. But water jet is not that expensive, and it can cut through a remarkably thick piece of material, up to an inch or an inch and a half. Cool processes. Electric discharge machining, otherwise known as EDM. Sometimes the machines are low tech, like a drill or a saw that we are familiar with and we use all the time. Or sometimes they're high tech, computer numerical controlled machines. And some are rough, some are precision. So let's take a look at some of those machines. Before we get into the different types of machines, what are some of the advantages of machining? As we mentioned, you can use any type of material. Sometimes those materials can be low cost and high quality. You can start with sheet metal. Remember, we've talked about sheet metal, starting material of choice, because it's the cheapest way to make a product. If you have any choice of starting material, you're going to start with sheet metal. It's cheaper than forgings, it's cheaper than extrusions, cheaper than castings, and so a lot of these machining processes are applicable to sheet metal. Machining it can be good for an excellent surface finish. It depends on which machining process we're talking about. But look at this. This is sand casting, where most of the surfaces don't matter. So you can leave the surfaces as a rough surface, but the flange faces need to interface maybe in a watertight fashion or an airtight fashion. There's a extra machined area here for a gasket, for a good seal. So only the flange faces, only the interfacing faces need to be machined, and they're going to have a nice surface finish, very smooth, and that's possible with machining. having an excellent surface finish. Machining is capable of high precision and tight tolerances, high accuracy, repeatability, pretty high production rates, definitely slower than some processes like die casting and sheet metal processing. So we're going to build, as we work through this, a summary of these 8 mechanical machining processes that we're going through. This table will continually expand downward as we talk about these different processes. And the aspects of the processes that we're going to cover here are the name, what is the process, the type of motion, so which parts move, the tool, the type of tool, does it have a single tooth or many teeth? When I say teeth, we're talking about the cutting feature, the cutting tool part of it. What kinds of parts is it used to make, and what are the approximate tolerances? So we'll start with the saw, very basic machining process. The saw, of course, the tool rotates. So we'll have a little icon for each of the machining processes here. So you know that the saw, the tool rotates, it has lots of little teeth on it. And each time one of those teeth interacts with the workpiece, it removes a little bit more material. And the tolerances are pretty wide. Here we say 0.8 millimeters. That may be good enough for some processes, like a lot of wood cutting processes, but for quite a few applications, 0.8 millimeters is not enough. Now, of course, there are saws that are capable of much tighter tolerances than 0.8 millimeters. Some you can cut and be accurate down to less than 0.1 millimeters. Some you are not even accurate to a centimeter. So these are just rough estimates of the tolerances. So here's an up-close view of the saw in action. It's working its way down through this metal, so the chip is coming off as a little curly comma-shaped chip. The characteristics of sawing are you get straight and contour cuts on flat or structural shapes. It's not good for really hard materials unless the saw is really hard, like with carbide teeth or diamond-coated teeth. Diamond, of course, is the hardest substance known to man. Some of these processes, if they're used to cut hardened steel, you need to have a really sharp or hard tip so that you're not losing material from your tool as you try to cut the workpiece. Of course, a saw only requires low labor skill, so that would be viewed as an advantage, making the saw easy to learn how to run. It's not difficult like maybe some CNC types of machining processes, and we mentioned the tolerances. Second here, drilling. As we build our list, in drilling, the tool rotates. That's similar to sawing, but of course we know that the drilling process is far different from sawing. The tool is usually a single point or abrasive type of tool, and it's used for making round holes of various sizes and depths. The tolerances can be pretty good, pretty tight for drilled holes. Here's our icon, our graphic of a drill. Let's look a little bit closer. And here we see the part of the drill called fluting, which are the spiral grooves on the tool for chip evacuation. So the chip, as it is created at the tip of the tool, slides up this fluting and then works its way outside. That is one of the important aspects of all machining processes, is that the chips have to escape. If there's no way for the chip to escape, the machining process is going to stop. And so drills, for 2 reasons, they have these flutes. Secondly, the cutting edge, as we look really up close on a drill, the cutting edge spins around and is creating that chip. So the fluting is the gap here so that the chip can actually form in the first place. And so this cutting edge is going to spin, the chip forms, and it slides up this fluting. Now sometimes those chips can be stuck in drilling, so that's why when you drill, you want to go down, and then especially when you're doing metal or soft materials, maybe even wood sometimes, you want to pull your drill out every once in a while, because sometimes those chips get stuck in the fluting and it's going to get hot. So you pull it out, let it cool down, get those chips out, and then you put it back, and you can go in and out to be able to make the process work better. I don't recommend just drilling straight down with no breaks. I would say about every 5 or 10 seconds, you should pull out. Not too often, not like every 1 second. You don't want to go in and out because you're not hammer drilling it. You're not wanting to hit it too hard. If you do hit it too hard, you're going to break your drill bit. So you want to pull in and out at reasonable times when the drill sounds like it's starting to get hot, get bogged down, get slowed down. So you pull it out so that you can clear out those chips. So drilling is also a low skill required, and because about anybody can learn how to drill, as long as you can accurately hit the target location, and you can have a really high production rate with drilling. Those are some of the advantages and characteristics of drilling. Thirdly, here, lathe turning. Lathe turning has two aspects: roughing, which is making the approximate shape, and then finishing. You can see a graphic here of roughing in action. So this is a screenshot from a video where the tool made stair step shapes, and then the tool later goes back and it smooths out the entire piece, making kind of the base for a doorknob. Lathe is also called turning and lathing and facing. Now, facing is when you use the lathe to make features on the end of the workpiece. So lathing is useful again for all types of materials. Lathing uses a single point or abrasive form tool. It takes a little bit more skill to learn the lathing process. So it does require skilled labor, has a low production rate, but with a programmed lathe, a turret lathe, or an automatic machine, it can require less labor. I know they use lathes or turners to cut a couple types of things commonly here in this market. One would be the turning of brake pads. So you can reface those brake pads and get some more mileage out of your brake pads. And of course, that operation doesn't necessarily have to have too much skill. You can have a simple program to reface and make the pad part of a disc brake, the disc part of a brake flat again. That's kind of a cool operation too. So the tolerances in lathes they can be rough, they can be fine, or they can be very fine in a final operation called skiving. Next, we have boring. So boring is actually a manufacturing process, not just the characteristic of my lectures. In boring, the part rotates. Like lathe turning, you have a single point that is in contact with the part cutting material, and it's used for cutting out internal surfaces or profiles. And the tolerances can be pretty tight. Some of us have heard of the boring process because this is known for boring of gun barrels, large and small. How do you make that internal space for to guide the bullet on its trajectory? It's called the boring process. So here you've got an inside hole, and this is spinning like on a lathe. And here you've got a single point tool. Here you see the tool is kind of a diamond shape. We'll see more about tools later, not in this lecture, but we'll talk a little bit more about machining tools later. So this boring bar, as this workpiece is spinning, this boring bar is going to go inside and it's going to cut away and make this hole larger and more precise. So again, boring is for internal surfaces or profiles. Characteristics are similar to turning. The boring bar, because it's long, it has to be very stiff to avoid chatter. Chatter is when it vibrates back and forth. It shakes because it's a long way from the holder. So that can be a pretty big issue. Even our students that did the lathe turning demonstration, they were experiencing chatter because as the wood was turning and they had their tool, there's a distance between where you hold the tool and where it interfaces with the wood that's turning, and you cannot hold it so tight that it cannot move. So that shaking or that movement is called chatter. Not only does that exist for human processes where you're holding it, that also exists for processes like this, where you have a boring bar and it's metal because there's no infinitely stiff material. There's no infinitely stiff boring bar that is not going to vibrate at all. Every material has its level of vibration. So chatter is something to avoid in lathe turning and boring. Next, we have milling. Here you see a schematic of the milling process. Milling is different from drilling. It looks the same because the tool's turning like this, but now either the mill is moving or more commonly, the workpiece is moving. So you see a label that says feed here. So the workpiece is moving and the mill is therefore removing material as the workpiece moves under it. So a mill has to have a lot of strength to resist that side-to-side motion that a drill doesn't. If you try to do that with a drill, because students try to do this all the time, they try to mill with a drill. What's going to happen? You're going to break the drill bit, and that's not safe because the drill bit can fly out and it can cut somebody. As I mentioned, we're trying to make a recording here, so I see a hand up, but let's do all the questions at the end. So that can be dangerous. Also, you can ruin the drill because it does not have a bearing that resists that side-to-side motion. A normal drill has a thrust bearing so that it can resist that thrust motion or that axial motion. Side to side, the normal force on the drill is going to put forces that a drill does not expect. We can't do manual milling with a drill. And we have a couple mills available in our laboratories, but they take, as we're going to see, they take quite a bit more training and skill to be able to operate. So some of the mill tolerances can be pretty tight. Let's look up close on the mill here. You have a bar, kind of like what you would have in a drill or in boring. You have a bar that comes down. Let me go back. So here it is. Okay, this is one type. Okay, this one looks kind of like a drill, but more commonly in each of these, they look almost like the flutes from a drill, but in each of these cutouts, you have an individual tool that's replaceable. That's the big reason why you see this kind of tool on a lathe and on a mill, because when this tool gets dull, it wears out, you replace this and you don't have to replace the whole bar, the whole tool holder. You just replace this tool insert. This mill is rotating here and it's producing this curly Q chip. And as it moves through here, this chip is going to fly outward. So you see the chips being created here, cute little cute curly Q chips, but it's because the workpiece is moving this way. The mill's not moving, just spinning. Of course, this is slowed way down. Speeds, these rotation speeds, are going to be much higher, but this is high-speed video. Milling is good for a variety of shapes involving contours, flat surfaces, and slots, a wide variety of tooling. It's very versatile. You can have low to medium production rates, and it definitely requires skilled labor. You can also have pretty tight tolerances. Since we talked about lathe turning and we've talked about mill turning, let's compare single tool, single point versus multi-point machine tools. So the lathe has one cutter interacting with the workpiece, whereas the mill, as it's spinning, it interacts with the workpiece at multiple locations. So a single point cutting tool has one main cutting edge versus multi-point has more than one cutting edge. Some of these mills can have hundreds of cutting edges on the cutter body. And the single point remains in constant contact. The multiple cutting points for multi-point tools like mills, they'll engage and then they'll disengage, engage and disengage. Single point can generate heat fast because they're always engaged with the material, kind of like I said, drilling. It's pushing, pushing, pushing. So you got to let it take a break to disseminate that heat. And then with milling or multi-point cutting tools, you kind of have a slower heat generation and tool temperature rise. We're going to see later why that's important. It's easier to design and fabricate single point cutting tools. Multi-point cutting tools are more difficult. A low feed rate is more common with single point. Higher feed rate can be done with milling, so you can get a lot more material removed a lot faster with milling. In single point, the material removal rate is low, and in milling and in multi-point cutting tools, the material removal rate can be higher. So here's some examples of single point and multi-point types of machining processes. We're getting close to our final processes that we're going to talk about among the 8 processes. And we're going to talk about these two together, planing and shaping. The main difference between planing and shaping, and planing the part slides and shaping the tool slides. These are good for surfacing and edging for external flat surfaces and contour profiles on large surfaces with pretty high tolerances. So here's an example of planing. So it's a sliding motion and it's cutting off a sliver of material, flat piece of material. So here's a shaping process. The workpiece is stationary and the cutting tool moves. Good for flat surfaces and straight contour profiles, suitable for low quantity production. The labor skill depends on the part shape. So here you see this, as I said, this one is a shaping process. So the workpiece is not moving, but the head here is going back and forth, and what comes off is a sliver of material. So in planing, the workpiece moves, good for large surfaces. In shaping, the cutting tool moves, and the amount of motion of the cutting tool is much smaller compared to the planing, the abilities of the workpiece to move in the planing process. So you have smaller surfaces capable in the shaping tool. So shaping, the cutting head moves. In planing, the workpiece moves. and the tolerances can be pretty tight. Quick summary of shaping versus planing processes. Again, I already mentioned in shaping, the workpiece is held stationary, and planing, the cutting tool is stationary. So in shaping, the cutting tool is moved, reciprocated, or slid back and forth. The tool is, whereas in planing, the workpiece is moved underneath the cutter. You have to have a quick return mechanism so that the workpiece can go back and forth in shaping. And in planing, you have to have a quick return mechanism instead on the workpiece. We talked about the bed motion. The shaper is traditionally a small machine. And the planer is a bigger machine because the whole work table has to move. The next process is broaching. Broaching is so cool. It's a tool with a lot of teeth that slides through and makes either a hole bigger or makes a gap bigger, makes an external feature bigger or an internal feature bigger. It's really cool. So in this one, this is a screenshot from a video as well. You see the oil going down inside here to cool and to facilitate the broaching process. So here's the tool going in and out and in and out. And as it goes down and up, it's removing and making these spline features into the shape that's desired. So broaching is good for external and internal flat surfaces, slots, and contours in 2 dimensions. This has the same profile in and out. Good for features that have no change in a 3rd dimension. The tooling can be costly, has a high production rate, and requires various amounts of labor depending on if the machine is pre-programmed. It doesn't require much skill in the labor, but it requires more skill for programming the machine. And then finally, of our 8 processes here, grinding and lapping. So in grinding and lapping, the tool rotates. You have an abrasive wheel. It flattens or smooths the surfaces and contours, and you can have really good tolerances because that's like a finishing process. Grinding starts out with a relatively rough surface finish. You got some different, you see grinding wheels here. These can be hooked onto a grinder like the one we have in the fabrication shop, or to a drill type of tool, depending on how you want to use the grinding media. Grinding is used to flatten or smooth the surfaces or to take off burrs. Burrs are the sharp pieces of metal left over from the other machining processes. And of course, we don't like those because they can be dangerous. They can cut or harm you. If we look really up close on the grinding media, we see the grains of silicon carbide or aluminum oxide, those abrasive particles. And when they scratch over the metal, they are scratching and removing. You see the metal pieces or the chips from the workpiece. So all these millions of sharp points from the rocks, basically, silicon carbide, diamond, aluminum oxide, they're scraping off a little piece of metal with every one. And so the bulk process is that metal is being removed in lots of different places at once. So grinding is a rougher process. You see the tolerances here, 0.4 to 0.2 micrometers of RA, average roughness. But lapping then has much finer media. We call the little rocks or the pieces that are actually doing the grinding or the cutting, those are called media. And so lapping uses a cloth with a slurry. So just a piece of felt, some kind of cloth, and you put a paste on it. And there's usually an oil or something to carry that paste on the cloth. And then that cloth is rubbed over the workpiece, kind of like polishing your car. What you want to get is that shiny finish at the end. And that's possible for pretty much all metals. And the tolerances on lapping are very, very small, very, very tight. Like we said, you can get a mirror finish with lapping and with polishing. So that means it has very, very fine tolerances. So lapping is known for its ability to produce very smooth and flat surfaces, making it suitable for precision components and optical applications even. Optical means reflective for lasers or glass for transparency, for visibility. So lapping and polishing are very fine grinding processes. So what to know from our overview of machining processes? Machining is the controlled removal of material from a workpiece to achieve a final desired shape and size. We talked about essentially 8 different kinds: sawing, drilling, lathe turning, boring, milling, planing and shaping, broaching, and grinding and lapping. There are also burning and erosion cutting processes like laser cutting that we talked about, and plasma cutting and water jet cutting. We talked about single point versus multi-point tools, and we saw some examples of each.